Hello and welcome to my talk. My name is Rastislav Sabo and today I'll be speaking about multi-cluster service deployments with operators and KubeCarrier. So before we start, let me introduce myself. I am a software engineer at Kubermatic, where I am working on Kubermatic Kubernetes platform and KubeCarrier open source projects. I am specialized on multi-cluster application management and multi-cluster networking. And in the past, I also contributed to several other open source projects such as Legato.io, FDI Go VPP, ContiVPP CNI, or Sysrepo. So, as the title of the talk suggests, it will be about multi-cluster service deployments today. During the talk, I will go through different aspects of multi-cluster service deployments, and I will also mention some community-driven open source projects related to them. We'll go through multi-cluster infrastructure management, then multi-cluster application management, and finally multi-cluster networking. At the end of the talk, I will also show a quick demo of multi-cluster application deployment with KubeCarrier and multi-cluster networking with Submariner. So before we go into any details, let me talk about use cases for deploying applications across multiple clusters. One of the reasons for doing that may be close user proximity. For example, we would like to serve users from different parts of the world without high latency. Another reason may be regional high availability, where we may want to minimize the impact of regional outages. Another reason may be security and organizational separation. For instance, we may have to use dedicated clusters per each organization or organization unit. The next one may be data locality. For example, databases with sensitive data may be only available in on-premises clusters. And last but not least, one of the biggest use cases is edge computing, where we usually run many smaller clusters distributed across multiple locations because of low latency requirements. So let's start our multi-cluster service deployment story with the necessary infrastructure for running and managing multiple clusters. For that, each cloud provider usually provides their own solution. But if you wanted to automate operation of many clusters across multiple regions and different cloud providers, including on-premises infrastructure, and do that all via a single pane of glass or a single API endpoint, I really recommend you to take a look at the open source Kubermatic Kubernetes platform, which can easily do it for you. Okay, let's assume that we have our hundreds or thousands of clusters running. Now let's talk about distributing some workloads on them. The Kubernetes SIG multi-cluster provides two possible solutions for that. The other one is called KubeFed. It aims to solve much more than just multi-cluster application deployment. For instance, it also aims to solve scheduling, DNS policies, etc. It is widely used but quite complex to use. The newer concept is called Work API. It is a simpler approach for deploying workloads to clusters. For instance, it does not cover cluster registrations or scheduling. But at this point, it is just the API definition without any implementation. It is based on the work custom resource definition, which can contain a list of resources that should be applied to a target cluster. On the right side of the slide, you can see how the work API custom resource may look like. It refers to a specific cluster, and in the workload manifests section, it contains a config map. Both approaches share some common concepts. They contain a single source of truth from where the workload manifests are propagated into managed clusters, and a control loop which applies resources and tracks their status. Now we are getting to the Kubecarrier project, which we created in Kubermatic. It builds on similar concepts as the previously mentioned solutions. There is one management cluster, which is our single source of truth. We call it a service hub. And there are multiple service clusters that can run application workloads. The difference is that by design, it only works with Kubernetes operators. Application operators run in the service clusters. Kubecarrier discovers their custom resource definitions and make them available for users in the service hub. And Kubecarrier then propagates the custom resources from the service hub to service clusters to drive the operators running in them. Finally, Kubecarrier has built-in multi-tenancy, So multiple service provider and multiple service consumer accounts are supported. The reason why we decided to use operators in Kubecarrier to build our multi-cluster application management platform is that operators help us to automate full application lifecycle within the cluster. That includes deployment, upgrades, backups, etc. And at the scale of hundreds of or thousands of clusters, it is really necessary to have this automation in place. Managing individual Kubernetes resources for each application in every single cluster just cannot work at this scale. This picture illustrates how Kubecarrier works from a high level. The service users interact only with the management cluster via Kubernetes APIs. They deploy custom resources derived from the original CRDs provided by application operators running in the service clusters. Kubecarrier then distributes those custom resources across clusters, which drives the operators running in them. And operators in the service clusters deploy and manage the application instances based on the content of the custom resources deployed by Kubecarrier. This slide shows how multi-tenancy works with Kubecarrier. As you can see, Kubecarrier supports multiple service provider and service consumer accounts, which are separated by namespaces. Also, users within each account get proper Kubernetes RBAC roles set up and assigned automatically. We have three personas illustrated on this picture. The platform operator operates the management cluster and manages the Kubecarrier installation itself, and also manages the Kubecarrier accounts. The service provider manages service clusters, operators running in the service clusters, and registers the services or their custom resource definitions in the service hub. The service consumers interact only with the management cluster, where they request and manage their service instances. Okay, so now we have our hundreds or thousands of clusters running, and we can automate the deployment of applications into them via our central service hub. Now let's talk about how the applications can talk to each other across these clusters. The Kubernetes SIG multi-cluster provides a solution for that as well, and that is called Multi-Cluster Services API. It extends the Kubernetes service concept across multiple clusters. In the provider cluster, services have to be explicitly exported using a service export custom resource. The multi-cluster services implementation that then propagates that service export into service imports in all clusters in the cluster set. And the exported service will then become accessible from each cluster in the cluster set at the DNS name, service name dot service namespace dot svc dot cluster set dot local. An open source project which implements this API is called Submariner IO. I will use this project in my demo. Okay, now I would like to show you a demo of multi-cluster application management with Kubecarrier combined with multi-cluster networking with Submariner. The demo topology would be similar to the picture that I have already described. We'll have one management cluster that we'll use as our service hub, and three service clusters where we'll be deploying our workloads. For the demo, we'll use the Redis database as our managed application. We will run Submariner across all four clusters to provide multi-cluster services connectivity. Okay, so what you can see here is the Kubermatic Kubernetes platform, where I have created four clusters, each one at a different cloud provider in a different region. One of the clusters I'll be using as a management cluster. That will be our service hub, through which we'll manage the deployment of applications into three service clusters. So let me go into the console. In the top left corner, you can see the management cluster. And then we have three service clusters here, service cluster 1, 2, and 3. The Kubecarrier has been already installed in the management cluster, and the service clusters have been registered in the Kubecarrier management cluster. Also, the Submariner have been installed in each one of the clusters, so the multi-cluster services should be working when we'll need them. So let me start the demo with showing you the Kubecarrier accounts that I have created. So we'll have three Kubecarrier accounts in this demo. One of them will be the service provider account, and then we'll have two tenant accounts. So the service provider will provide Redis service to the tenants. In each one of the user clusters, in service clusters, I deployed the Redis operator already. But so far, no Redis instances are running in any of those clusters. At this point, we can check via kubectl get catalog entry that Kubecarrier has already discovered the custom resource definitions in the service clusters. So in our catalog entry list, we can see Redis in cluster 1, Redis in cluster 2, and Redis in cluster 3, which are ready for using by our tenants. So at this point, our tenants can request an instance of Redis in any of those service clusters. And the way how they can do it is by creating a custom resource, which is derived from the original Redis custom resource definition. But the API version refers to a particular cluster and a particular service provider. So in this case, by using this custom resource, we'll deploy a Redis instance in service cluster 1. And the spec of this custom resource contains some information needed to deploy a Redis instance, such as password for accessing the database that we'll use later. So let me now use this deployment YAML file and deploy a Redis instance in the service cluster 1 as a tenant A. Uh, to make sure that we can see what happens, I'll run a watch commands here in the service clusters 1, 2, and 3. They'll be watching for all pods, and we are grabbing the name Redis in across all the pods. So I'll now go ahead and fire this command. So again, we'll apply this custom resource, which refers to cluster 1 under tenant A, and that will create a Redis instance for our tenant. So soon we should be able to see that the Redis instance has been deployed for tenant A in the service cluster 1. Similarly, we can request a Redis instance for the tenant B. So using the same custom resource under tenant B user, we can request a Redis instance for the tenant B. And as you can see, it has been just started. And very similarly, we can also deploy some Redis instance in the service cluster 2. So the deployment manifest would look exactly same, apart from the API version where we refer to service cluster 2. So let me deploy that one as well. And we should see in the service cluster 2 that our Redis instance has been started. Okay, at this point, we have 3 Redis instances running in 2 different clusters. Now let's try to connect to those Redis instances from a different cluster. So in the cluster 3, we are not running any Redis instance. And potentially we could try to connect to those Redis instances from this cluster. So in order to do that, we can rely on multi-cluster services API, which is implemented by Submariner, which is already installed in our clusters. And so in order to export the service to a different cluster, we should first review what are the existing services of our Redis instances. So as we can see, we have a Redis instance service in the tenant A namespace, which is of type cluster IP. And similarly, we have a Redis instance service in the tenant B namespace, which is of cluster IP type. So in order to export them to other clusters in our cluster federation, I would use the command subctl export service. Subctl is a binary provided by Submariner, but essentially what it does is that it deploys a service export custom resource with the name, with the service name, Redis instance, and the namespace as given here. Similarly, we can also export the other service instance in the tenant B namespace. And at this point, we should be able to verify that service exports have been properly created by issuing kubectl get service exports. And yes, as you can see, our Redis instances in tenant A and tenant B namespaces have been exported. Similarly, we can do service export in the cluster 2 for the Redis instance running in there. And again, we can verify that service export custom resources have been properly created in this cluster. At this point, in the cluster 3, we should be able to see the service imports automatically created from the exported services in cluster 1 and cluster 2. And as you can see, kubectl get service imports gives us 3 service imports, 2 in cluster 1 and 1 in cluster 2. So now we should be able to access any of those 3 services from this cluster. So let me exec into a client pod running in this cluster. And the way how we can connect to those services is using DNS names that refer to original service name, original namespace, dot service dot cluster set dot local. So this domain name we should be able to resolve right now, and it seems that resolving works. So we can go ahead and try connecting to the Redis instance with the Redis CLI tool. We are just referring to the exactly same domain name, and we are using the password that we specified in our Redis custom resource up here. So this should work, and if it works, we should be able to run a ping command and we should get the pong from the server. Right. Exactly same way we can also verify the connectivity to the Redis instance in the cluster 2. So it should just work as for the Redis instances in the cluster 1. Okay, that was it for the demo and for my talk as well. If you have any questions, feel free to contact me at this email address or via Slack right after the session. And thank you for watching my talk.